Hello students, I'm glad to be with you today. In today's class, we'll be learning about distribution of molecular velocities. The distribution of molecular velocities. Now, gas molecules are moving randomly in a straight line with different velocities due to collisions with each other and with the wall of their container. Now, this is one of the postulates of kinetic theory of gases. And the distribution of molecular velocities also is actually the foundation for this kinetic theory of gases. Now, at any instance, some gas molecules will be moving extremely fast, while others will be moving at an extremely slow velocity. But majority of the gas molecules have an average velocity. Therefore, it is not possible to determine a single value for the velocity of a gas molecule. Hence, the distribution of molecular the distribution of velocity is considered instead of a particular velocity. And now when we plot molecules of this gas against their velocity in a graph, what we get is Maxwell-Boltzmann distribution. Now that name Maxwell-Boltzmann was actually coined from the name of two of the influential physicists that contributed to bringing about the distribution. Now the first one, Maxwell, his full name is James Clerk Maxwell. He's a British physicist. And then we have an Austrian physicist also by the name Ludwig Boltzmann. Now, it is these two guys, or these physicists, working separately. They were not working together. That showed theoretically, and it has since been demonstrated experimentally, that molecular speed are distributed. So that means we won't be talking about just a single speed for a gas molecule, but that at a particular temperature also the velocities are what are distributed, are spread. So the Maxwell distribution is a theoretical relationship that predicts the relative number of molecules at various speed for a gas at a particular temperature. Now this is the foundation of the kinetic theory of gases. Now what you can see on the screen there is the Maxwell-Boltzmann distribution curve, which shows the distribution of molecules at different velocity in a gas. You can see fraction of molecules on the y-axis and then velocity on the x-axis. Then you can see the velocities there. You can see 0, 200, 400, 600, 800, 1000 and 1002. Now the Maxwell-Boltzmann distribution curve shows the distribution of molecules at different velocities in a gas. Now this distribution also can be used to determine the distribution of kinetic energy for a set of molecules. This means that the distribution of the kinetic energy is identical to the distribution of molecules of the velocity for a certain gas at any temperature. So that means when we're talking about distribution of molecular velocity, we're also talking about distribution of what? Of kinetic energy. Now, the distribution is often represented graphically with particles, with the particles or molecules on the x-axis, particles, and then the relative number of particles on y-axis. Okay, the molecular velocity. The molecular velocity or the particle velocity on the x-axis, like you can see that the velocity on the x-axis, while we have the relative number of particles or molecules on the y-axis. Now, Maxwell-Boltzmann equation. Now, the distribution we just saw has an equation, and the equation is given by the n over n equals to 4 pi v squared bracket open and then close m over 2 pi x 2 pi kbt exponents open bracket minus mv squared divided by 2 kbt close the bracket dv. Now, where the n over n is the fraction of molecules moving at a velocity v to v plus dv, which shows the increase of in velocity, while m is the molar mass of the molecule, kb is the Boltzmann constant, which is given by 1.380649 times 10 to the power minus 23 joule per Kelvin, and then T is the absolute temperature, that is temperature in Kelvin. The equation is used to determine how many molecules of gas are there which are moving between the velocities, okay, from v to v plus dv. Now, at a velocity 0, Maxwell-Boltzmann distribution gives us that the n over n equals to 0. That is, there is no molecule which has 0 velocity. Okay, so gaseous molecule do not have what 0 velocity, and this is in accordance with the theory that says there is no molecule in gaseous state. There is no molecule in gaseous state which is not moving. So every molecule in gaseous state is what is in constant random motion, like we've mentioned earlier when we began the lesson. The distribution of speed depends on the temperature, and as the temperature increases, so the average speed also increases. Now, 3 velocity terms that were derived from Maxwell-Boltzmann distribution that we'll be considering in this lesson are most probable speed, average speed, and root mean speed. And then from the graph, you will see that the most probable speed is less than the average speed, and then the average speed is less than the root mean square speed. We'll be going into the detail of each of these speed or velocity expression as we proceed. The most probable speed is the speed or the velocity at which the maximum number of molecules exists, or the speed at the peak of distribution. You can see the peak of the distribution here. You see, this is the point where, if you look at it, the area inside is the represent the molecule. So where the molecule is at the highest or peak or maximum is what is known as the most probable speed, and it is given by this formula v equals to 2r3 over m, all in square roots. Then the average speed is the sum of speed of all the molecules divided by the number of molecules, and it is given by v equals to v1 plus v2 plus v3 plus divided by n, and it's also given by the square root of 8rt over pi times m, where r is the gas constant, T is the absolute temperature, and then m is the molar mass of the gas. Then the third velocity expression that we'll be looking at is the root mean square speed. Now, what is the root mean square speed? It is a type of average molecular speed, okay, which is equal to the average molecular kinetic energy, and it's also the square root of the average of the squares of the velocities. So now these are the 3 terms, and then you can see it is given. You can see the formula for calculating the root mean square velocity or speed, and then that of average speed, and also that of the most probable speed. So we'll be concentrating on that. Now, the slope of the curve changes for gases at different temperatures. So at different temperatures, we'll see that the slope of the curve is what of the distribution of the Maxwell distribution curve what changes. Now, for instance, if you look at the distribution here, we discuss like it is normally done. We have the fraction of molecule on the y-axis and then the velocity on the x-axis. Now, if temperature of the gas increases, its average kinetic energy also increases, as we can see. Okay, more molecules will have higher speed and fewer molecules will have lower speed, and distribution will shift towards higher speed overall, that is to the right. You can see, look at, as temperature increases from 100 Kelvin to 200 Kelvin to 500 Kelvin to 1000, you discover that this the curve now is what is shifting towards the right. Is shifting towards the right to show that the distribution is shifting towards what? Towards high speed, because you can see towards the right is, for example, from 0 to 500. As we move towards the right, we have 1000. As we move towards the right, we have what? 15. You can see the temperature at 1000 Kelvin. Look at how it spread from 0 down to almost 1500. So this shows how the slope of the curve changes. Exactly. Now, in the same vein, if the temperature decreases, average kinetic energy also decreases. Okay, molecules will have lower speeds and fewer molecules will have higher speed, and the distribution will shift towards the lower speed overall, that is to the left. And this behavior is illustrated for nitrogen gas in the figure above. Now you can see that, you see, for lower speed, now when you move from 100 to 500, you can see that the curve is shifting towards the left. Okay, that means to 200 to 100, you can see, and you see the curve again. You see, for at higher temperature the curve flattens and is or broaden, okay, compared to when it is what, when the speed is what, when the temperature is what, is low, like 100 Kelvin. Now you can see how it is narrow and steeper compared to the at 1000, when it is what, when it is broad and flattened or broadened. Okay, so but in all, the area under the curve gives the total number of molecules in a gas. So a fixed amount of gas molecule remain constant at all temperature. So the total number of molecule is the same at all the temperature. So the total area under each curve is equal, because it's the same amount of what, is the same number of molecule of what, of nitrogen gas. So now, what is the importance of the distribution of this molecular velocity of gas at different temperature? Now, the importance is that it can be used to explain how temperature affects rate of reaction. Now, let's look at some explanation of how increasing temperature increases the rate of reaction. You see, looking at this distribution curve here, you see at T1, that is at the lower temperature. T1 is the low temperature, while T2 is the high temperature. We say increasing temperature increases the kinetic energy of the molecule. We have mentioned that before, and therefore more molecules will be expected to have higher velocity at higher temperature. If temperature increase, kinetic energy will also increase, and more molecule will be expected to have what, higher velocity at higher temperature. Now, increasing the temperature also shifts the curve to the right. You can see how when the temperature was increased from T1 to T2, there is a shift towards the right. Is that taking? And then the curve is also broader. The curve near the maximum is broader for the higher temperature than for the lower temperature. Is that taking? And what does that indicate? It indicates that more molecules now possess higher velocities. See, and more molecules have an energy greater than the activation energy. You see like the T1. Look at the activation energy, where we have this green shade here. You see this green shade now shows the activation energy. Okay, this is the activation energy when it is what, T1. But at T2, look at the activation energy look at the oxygen energy, you can see there's a raise here, which now shows that more molecules here will possess higher velocities, and when more molecules have an higher energy greater than the oxygen energy, it will result into what more successful collision will now occur per unit time, and by so doing there's going to be what increase in the rate of reaction. Now the next one, we'll be looking at explanation of how addition of catalyst increases the rate of reaction. You see from the graph here, we see the oxygen energy when there is no catalyst, and then the oxygen energy when there is catalyst. You see, now what does catalyst actually do? Catalysts provide an alternative reaction pathway or route with a lower activation energy. You see, when look at the activation energy here at this particular velocity, okay, and kinetic and energy. You see, but when catalyst was added, you can see that there is a lowering of the activation energy, and you know that the activation energy is the energy that is required to the energy barrier that is needed to be overcome before a reaction can take place. So when the activation energy was at this point where there is no catalyst, you discover that there are only few molecules is that taking that can that can result in collisions. Is that clear? But with the help of catalyst, the catalyst help to do what? Change the pathway by reducing the activation energy. By using the activation energy, the activation energy is now here. So with that, we can see that there are more. This now shows that there are more molecules in excess of the lower activation energy, and with that, this results in what? More successful collision, okay, per unit time, and thereby increasing the rate of reaction. Because when we have more successful collision, then there will be there will be increase in the rate of reaction. Then the next one, we'll be looking at the molecular velocity. How molecular velocity is directly related to molecular mass. We can see from this typical example here of noble gas, where we have helium, neon, argon, krypton, and xenon. You see, at a given temperature, you see light molecules, that is molecule with low molar mass or low molecular mass, tend to move faster on the average than heavier molecule. You remember in kinetic energy, one of the postulates, I think the fifth postulate, states that the lighter molecule move faster than heavier molecule. Okay, lighter molecule move faster than, and why is that? Because lighter molecule, they have low molar mass, and since they have low molar mass, they have high average speed. And with that, there is a wide or broad spread of speed. Just take a look at helium. Look at how it spread from 0 down to about 300 meter per second, okay, for the velocity. You can see it is broad, it is broad, it is wide, broad, and there is high velocity. So there's distribution of high velocity here. Is that taking? Why? Because helium is a light molecule. It has low molar mass. Now compare it with xenon, for instance. You know helium has just 4 points, about 4. The molar mass is 4. But look at xenon with a molar mass of about 131.3. You can see how the curve, the curve is steeper and very narrow, and it's just a little above 500 meter per second. When xenon, when helium or neon, helium or neon are getting to, helium for instance is getting almost up to about 300 meter per second, and helium is getting above 1000. Xenon, krypton you can see that their curve does not exceed was does not exceed 100 meter per second. So this shows all that what the heavier the molecule, the less the speed. Okay, why the lighter the molecule, the higher what the higher the speed. Now we'll be going into our work example, and our first work example says calculate the values of the most probable velocity, that is VMP, also the average velocity, as well as the root mean square velocity. These are the three velocity term or expression that we say we'll be emphasizing on in this lesson. Okay, so we're looking at that of a nitrogen molecule at 27 degrees Celsius. Now, to do it, all you need to do is to collect all the variables and the constants, and then substitute them in the formulas that were presented with earlier. Okay, now we have temperature, and we have mentioned earlier that molecular velocity is dependent on temperature, but independent of other things like pressure. Does not depend on pressure. For example, if assuming we have pressure as one of the value here, now we will not make use of it because it does not depend on pressure. As you can see, even from the formula, there is no place where we're given pressure, because there are some questions that you will see and there is pressure will be given to you, but you will not be making use of it because because molecular velocity is independent of pressure. So what do we need to do? So first, we have our temperature, which is in degrees Celsius. So we need to convert it to what? To absolute temperature, which is in what? In Kelvin. So what we need to do is 27. By the time you add 273, that is the conversion factor. Okay, it gives us what? 300 Kelvin. And for the molar mass, you see nitrogen, the molar mass of nitrogen is what? Is 14. Now, but for nitrogen molecule, you see, nitrogen is just one, but nitrogen molecule, that is N2. That means we're going to multiply the 14 by 2. So when we multiply 14 by 2, we have what? 28. So we have 28 gram per mole. Now, it's in gram per mole. Now, but we need to convert it to what? To kilogram per mole. You may ask why. I will let you know later. You see, so convert this 28 gram per mole to kilogram per mole by dividing it by what? By 1000, since 1 kilogram equals to 1000 gram. Now, the next one is what? Another thing that we need is what? Is R, which is constant, which is our universal gas constant. Now, it is given by 8.314 in kilogram meter per second. Now, you can see, then per Kelvin per mole, you can see that our gas constant here is in what? In kilogram. So if our gas constant is in kilogram, has kilogram in the unit, definitely our molar mass also should be converted to what? To kilogram. Okay, so this is very important, because if you use a different unit, there's going to be some conflict and you may not be able to get the right answer. Okay, then these are three formulas that we'll be making use of: the most probable velocity formula, the average velocity formula, and the root mean square formula. Then let's start with the most probable velocity. So we put all the given value and constants, that is the variables and constants, in the most probable velocity formula. So we have 2r3 over m. We have 2 r is given by 8.314 times our temperature, which is 300 Kelvin, divided by our molar mass, which is 0.028. So when you multiply 2 times 8.314 times 300, you see, we are going to get 4988.4 divided by 0.028. So when you divide it, we get what? 178,157.1429. You see, when you look for the square root, now when you find the square root of 178,157.1429, you get 24. we get 422.087, and then when you approximate to the to 3 significant figure, we get 422 meter per second. So the most probable velocity of nitrogen molecule is 422 meter per second. Then to get the average velocity, we also recall the formula and then input our value, or substitute our value for R, T, and M and pi as well. Our pi is given to be 3.14. So 8 multiplied by 8.314 times 300 divided by 3.14 times 0.028. Now when you multiply the numerator, that is where you have 8 times 8.314 times 300, we get 19953.6. Divide by the denominator, and what do we get in the denominator? We have 3.14 multiplied by 0.028, and then we get 0.08792. Now when you divide 19953.6 divided by 0.08792, we now get 338,655.8045, and the square root give us 581.941. See, when you approximate it to the photo 3 significant figure, we have what? 582 meter per second. So the average velocity of nitrogen molecule is 582 meter per second. Then the last one is to calculate the root mean square velocity. So we'll do the same thing by plugging the data collected in its formula. And what is the formula for root mean square velocity? Is 3RT over M. So when we substitute for R, we have 8.314, and then we substitute for temperature, we have 300 Kelvin divided by 0.028. So multiplying the numerator, the value in the numerator, we have 3 times 8.314 multiplied by 300 divided by 0.028. At the end of the day, we are going to get 7482.6 divided by 0.028. Then when we divide, we get 267235.7143. Then square root will now give us 516.9485. Then when we approximate that to 3 significant figure, we have 518 meter per second. So our root mean square velocity for nitrogen molecule is 517 meter per second. Now we'll be going into our class activity, and in the class activity we have about 5 class activity which is intended to help you check your learning, okay, to ensure that you have actually understood all that we have done. So the first one is to calculate root mean square velocity of nitrogen molecule, but at 25 degrees Celsius. And then the answers have been provided. You choose the right answer. Then the second one is to calculate the value of most probable velocity, average velocity, and root mean velocity for xenon. You know, the one we did in our example is for nitrogen, so we are going to do it for xenon gas at 298 Kelvin. The answers are also being provided. Then you are given the constants. Here you are asked to use 8.3145 as your gas constant, and then 3.14 as pi. Then the third question says you should so there is a diagram there that is presented below, which is Boltzmann distribution of molecular velocity. So you have to add a curve to the diagram. We have one curve now, T1. Add a curve now, that is T2, to show the effect of increasing temperature, okay, on the Boltzmann distribution. And then the B part is explain how increasing temperature increases the rate of reaction, making response to the Boltzmann distribution of molecular velocity. Then the fourth question is the diagram also asks, there is a diagram of Boltzmann distribution of molecular velocity, and then you are asked to label the diagram with activation energy of reaction with and without catalyst. Then explain how addition of catalyst increases the rate of reaction. And then the last one is to calculate the average velocity of gas system whose number of molecule and velocity are given below. So we have our velocity, we have the number of particles. So you can use the formula of average velocity, where you need to add all the velocity and also add the number of molecules. Then after doing that, the B aspect. Wow, we have come to the end of the class today. In the next class, we'll be having another interesting concept in chemistry to learn. Until then, I remain your facilitator, Sunday Ibrahim. Thank you.